can analyze exactly what makes different kinds of chemical relationships work, and that's what this episode is all about. But people, please remember that we here at Crash Course do not dispense relationship advice. First things first, why do atoms do this at all? Well, like everything else in the universe, atoms do whatever they can to reduce their overall energy. And they reach their lowest energy by achieving a balance between attractive and repulsive forces, being neither too clingy nor too aloof. So when two atoms approach each other, the electrons of each are attracted to the protons of the other. This is the electrostatic force. Like charges repel, opposites attract. Like in real life, or at least Paula Abdul songs. I know, I'm old. So when one atom is attracted to another, just like Edward Cullen and Bella in chemistry class, to use a slightly more timely reference, it gets stressed out by the attractive force and tries to relieve the stress by getting closer. We've all been there, right? That hot, nerdy vampire girl in your chemistry class, it's intense. The pull is so strong that the stress level or energy rises when the two are separated, so they stay close. But sometimes they can get a little too close. When that happens, the nuclei repel each other because of their like charges, and the energy between them rapidly increases, and they both back off just enough to find that perfect little distance between them, and everyone relaxes. This ideal, wonderful distance is the bond length. It's the distance between two nuclei at the point of minimum energy. In other words, where the attractive and repulsive forces cancel each other out. The distance at which these two atoms of chlorine reach their minimum energy, caught between the attraction of the electrons to the nucleus and the protons repelling the nuclei, is the bond length. That energy minimum, which we know absolutely is negative 239 kilojoules per mole, occurs when the distance between the atoms is 0.00199 nanometers. That distance is the bond length of Cl2, chlorine gas. Now, because the electrons are attracted to both nuclei in the molecule, they actually spend the majority of their time in the space between them. This is often described as sharing electrons, and we call this kind of bond a covalent bond. But not all sharing is equal. I should know, I have an older brother. The strength with which an atom holds shared electrons is called its electronegativity. The electronegativities of various elements are all super well known and waiting for you in tables on the internet. If two atoms in a bond have very different electronegativities, like say hydrogen at 2.1 and oxygen at 3.5, the electrons are more attracted to the atom with the higher electronegativity. The difference is so great that the electrons spend most of their time around the stronger atom and much less time around the other one. Like how all of the neighborhood kids wanted to hang out with John, my older brother, because he was more charismatic. When the electrons hang out closer to one side of the bond, it creates a slight negative charge in that area and a slight positive charge around the other atom. This separation of charges is called polarity. And it's the polarity of the molecule that these atoms form, H2O, that makes water the most important molecule on Earth. Covalent bonds like this, where electrons are attracted to one atom more than the other, causing a separation of charges, are called polar covalent bonds. But when a covalent bond forms between two identical atoms, like the two chlorine atoms in our graph earlier, the electrons are distributed evenly. We call this a nonpolar covalent bond. But you've also got to consider the middle option, where the atoms aren't identical but have very similar electronegativities, like hydrogen with an electronegativity of 2.1 and sulfur at 2.5. The difference here is so tiny that the electrons are pretty much still evenly distributed, and we call that a nonpolar covalent bond as well. There's a huge world of important chemicals that have these kinds of bonds, so many in fact that we will dedicate a couple of separate episodes to them. Covalent bonds tend to form from nonmetals and sometimes metalloids, those elements that have both metallic and non-metallic characteristics. That's because most of them hold their electrons so tightly that they're more likely to share them with another atom than to gain or lose them altogether. Metals, on the other hand, have loosely held outer electron shells, so they're constantly dropping electrons and becoming positive ions. And when positive ions come across negative ions, like those formed from halogens, for instance, you have to know what's gonna happen. They're attracted to each other, which means energy is required to keep them apart, which means that they're gonna bond if they can, creating that oh-so-wonderful point of minimum energy. This type of bond is unsurprisingly called an ionic bond, a bond formed between a positive ion and a negative ion. Because the ions are formed when one atom loses electrons and the other gains them, we often say that an ionic bond is formed by the transfer of electrons from one atom to another. And we can calculate the amount of energy that exists in a bond between ions at a given distance using a formula called Coulomb's law. Note that this only works for ionic bonds because the calculation requires the charges of the ions, which covalent bonds don't have. Coulomb's law says that the energy between two ions equals the product of the two charges, which are represented by capital Qs, because why not, divided by the distance or radius between the two nuclei, all multiplied by a constant. 2.31 times 10 to the negative 19th joules per nanometer. Of course, the radius also has to be expressed in nanometers, you gotta make the units match. Let's see how it works with something simple, sodium chloride or table salt. We know that the normal charge on sodium ion is +1 and the normal charge on chloride is -1. These are Q1 and Q2. The length of a stable NaCl bond is 0.276 nanometers, so we put that in for the radius. And finally, a quick calculation tells us that the bond contains -8.37 times 10 to the negative 19th joules of energy. Remember that negative number represents a decrease in the energy of the system due to an attractive force, which certainly makes sense here. Sodium and chloride ions are strongly attracted to each other due to their opposite charges. Of course, you might have noticed that -8.37 times 10 to the negative 19th joules looks like a tiny number, but keep in mind we're talking about one single pair of ions. The -239 kilojoules that we got for chlorine, that was for a whole mole of molecules. When multiplied by the 10 to the 17th or so ions in a single grain of table salt, and then by the thousands of grains of salt in a mole, the energy becomes much more significant. The NaCl bond is in fact quite strong. And because they consist of a positive ion and a negative ion, two charges completely separated between two different particles, ionic bonds are extremely polar. Way more polar than polar covalent bonds. And so those are our three types of bonds. Nonpolar covalent, formed by the equal or nearly equal sharing of two electrons between nonmetal or metalloid atoms. Polar covalent, formed by the uneven sharing of electrons between two nonmetals or metalloids. And ionic, formed by the transfer of electrons from a metal to a nonmetal. It's important to remember, though, that there aren't only three designations for chemical bonds. Just like human relationships, bonds don't always have really well-defined boundaries. Everything is a continuum. Labels are useful, but they can only take us so far. There are, however, certain properties that each kind of bond tends to have that you should know. For instance, ionic compounds are often crystalline in their solid form because of the way the ions pack together, like salt is. They're generally soluble in water because the two ions interact separately with the positively and negatively charged areas on a water molecule, and once they're separated or dissolved, the ions allow the solution to conduct electricity. Covalent compounds, on the other hand, tend to be softer solids, liquids, or gases like Cl2 is at room temperature. They're often not soluble in water, and even when they are, the solutions don't conduct electricity. The difference in these properties stem mostly from the differences in their polarities. So yeah, polarity is crazy important. So important that we'll be doing a whole episode on it soon. Until then, I want to thank you for the bond that you have to Crash Course Chemistry, whether it's casual observer, faithful viewer, or committed subscriber. Today, if you were paying attention, you learned that chemical bonds form in order to minimize the energy between two atoms or ions. You've also learned that the chemical bonds may be covalent if atoms share electrons, and that covalent bonds can share those electrons evenly or unevenly. Bonds can also be ionic if the electrons are transferred, and you learned how to calculate the energy transferred in an ionic bond using Coulomb's law. This episode of Crash Course Chemistry was written by Edie Gonzalez and edited by Blake DiPastino and myself. Our chemistry consultant is Dr. Heiko Langner. It was filmed, edited, and directed by Nicholas Jenkins. Our script supervisor is Michael Aranda. He is also our sound designer, and our graphics team, as always, is Thought Cafe.